Okay, on to part C of this problem, where we're going to revolve this solid about the y-axis. So again, first thing we want to do is think about what that means. We're going to take this region R, highlighted in green here, and we're revolving it sideways now about the y-axis. And so now I do have a 3D model I'll show you in a second here, but now our little rectangles are going sideways across here. And, like we could find the area that way too. In part A, we found the area. We did it vertically. We had all of our rectangles going vertically and integrated with respect to x because the width of the rectangles was dx. It was a little change in x along the x-axis. Now what we're doing is thinking about it the other way. We're thinking about it sideways so that the width of these rectangles is a small change in, not x, in y. Okay, it's a change along the y-axis, this little width here, right? And then the length of these rectangles is a difference in x values of the curve. So this curve and this curve, it's the difference in those x values. So we're actually going to have to solve each curve for x in terms of y. And we're going to integrate with respect to y. We're going to use the inverses of these functions so that it's with respect to y instead. But also, there's another complication on here. And this is why I mentioned in another spot that this problem is actually better done with another method called the shell method. But I like it for this because I think it helps you to understand how these are put together. So we're going to use the washer method and disk method still. The shell method, though, is a way of revolving about a vertical line like the y-axis, but still doing everything with respect to x. It's something I might talk about in another video. I may do this problem, but it's not part of the AP curriculum. You don't have to know it for Calc AB or BC. We're going to stick with disks and washers here. They probably would not give this question on the AP exam because this one is better done with another method, the shell method. And since shell is not part of the curriculum, they would avoid that situation where that's better. Anyway, at least from my experience. I don't know. I don't speak for AP or anything. What's tricky about this is from a y value of 2 up to a y value of 4, it's what I was showing you. It's these rectangles have this curve, which was our g of x, y equals g of x curve, and this curve here, which was our y equals f of x curve, as the boundaries. So, we're looking at this one, g of x, except we'd have to get the inverse, so really g inverse of y, minus this one, because it's the bigger x value minus the lesser x value. That's for above that horizontal line I just drew. And in fact, let me change them from f of x and g of x, from y equals f of x and y equals g of x. Let me write those as inverses just to make my point clear here. What we really want, this curve, it's still this g of x function, right? But if we solve for x, it'll be x equals g inverse of y. And it's actually, since it's just y equals x, it's just x equals y. That is the inverse of y equals x, right? It's its own inverse. This one's a little more complicated than that. We want x equals f inverse of y. Now, you don't have to write it that way. What you do is you take this function, y equals the square root of x plus 2. I wouldn't switch the variables. You probably learned in algebra class to find the inverse, switch the x and y and solve for the new y. No, just solve for x. Just solve for this variable x and keep it as x though, okay? So we're going to subtract 2, get y minus 2, and then we're going to square both sides. So y minus 2 quantity squared equals x. So that's this inverse function over here. So instead of calling it x equals f inverse y, let's just call it x equals y minus 2 quantity squared. Okay, and so the point is we're taking this x value, which is x equals y, minus this x value, which is x equals y minus 2 quantity squared. That's above the horizontal line. What's tricky about this problem is that we need two separate sets of boundaries here, two separate integrals, because below this horizontal line, the boundaries are now still this function, the one that came from g, But now we're not using the square root function anymore because it doesn't extend down there, what we're looking at. It's this vertical line, which is actually x equals 0. So now we're going to use x equals 0 and x equals y. So from 0, a y value of 0 up until a y value of 2, we're going to use this one. And from a y value of 2 up until a y value of 4, we're going to use these two boundary functions. Okay, and that's our game plan here. But what is this going to look like? Let's take a look at that next, and then I'll come back to this. So here, I've got the same region here. I showed in part B this whole thing with the around the x-axis, right? So now we're looking at it about the y-axis. I've drawn the line y equals 2 in red there so that you can see it splitting up the region. Okay, and what we're going to do, I also, here, let me just kind of show this. If I didn't set up my barriers here, that's working. Why is this one not? There we go. Maybe if I scroll this down a little. There we go. Okay. So you can see that full parabola a little bit more now. But I really only, that parabola, the bottom half of it, like that part that's disappearing now, that part isn't there, right? It was just the top half of the parabola. So it's really only valid from a y value of 2 up until, really until a y value of 4. Right now it's going till 5. But if we go to 4, I just had it and then let it go. That's where that boundary is now, like above the horizontal line. Okay, and then below the horizontal line, it's just x equals 0 that we have. In fact, I could graph that, but I won't right now. So when we look at the top half here, it looks like this. You can see that region being revolved about the y-axis. And you can kind of see inside there because I didn't put the back on it, but that would all be kind of filled in between there as it's a solid, okay? And then the bottom half is actually just a cone. Let me show that only. It's a cone because let me make it go away here. If you look at the bottom region there, it's just below the red line and between the purple line and the y-axis there, it's a triangle. And you're revolving that triangle about the y-axis. So like it's this part right here, right? If we revolve that about the y-axis, you just get a cone, right? Cone right in there. And so I know it's not that great to look at on this drawing, which is why I'm using Desmos here. But I probably need to do some work on this graph a little to make it a little better. But there's the cone. With that bottom half. Let me just show again without the cone. Picture that triangle revolving about the y-axis, and now with the cone, there it is. It's filled in, and then the top half again. There's that, and so the bottom part below the line y equals 2, it's like solid all the way through. But then above y equals 2, you have this kind of cavity in the top of it that you can see here, and let me show it from a different angle here, and we can kind of look at it in there. And that's what we're finding the volume of, that solid. Okay, so here it is looking at the xy plane, and here it is on a little bit of an angle, although that's kind of the opposite side from where I want to see. So that's what it looks like. All right, there's the y-axis, and yeah, I don't know, now it's all screwed up. There's the x-axis. Maybe I should just do this and rotate it a little from there. That's probably for the best. Okay. All right, so let's look at how to do it. Back to our 2D drawing here. Again, what we're going to do is we're going to take these rectangles, and it's two separate integrals. We're going to go one from like 0 to 2, and we're going to take a rectangle here and revolve it about the y-axis to make a disk. Now, this is technically called the disk method now, not washer, because there's no hole in it, right? So if you take the washer was when you had a small hole in there, and it was the area between the two circles with this infinitesimal width, which we were calling dx when we did it vertically, and now when we do it horizontally, it's going to be, that width is going to be dy. So the washer has a hole in the middle. A disk is the same exact thing except no hole in the middle. So the disk is solid all the way through. So on the red part of my graph on the right of where I'm drawing right now, that's solid all the way through. There's no hole because my left boundary is x equals 0, which is the y-axis. It's the axis we're revolving around. So it's touching that axis of revolution the whole way, and that's why we're going to get a solid cone here when we revolve it. Okay? Then above the line, when we do the blue part, we're going to take this rectangle, the ith subinterval, which represents all of the horizontal rectangles going across this region in blue here, and we're going to revolve it about the y-axis. And when you do that, that's going to make that washer shape with this hole in the middle, right? That's not the part is going to be in our solid. That's the hole. This is the shaded region that's going to be in our solid, right? That washer. So that's the setup. Okay, let me get that out of there because it's cluttering up the graph. So here's what it looks like algebraically. I'm just going to scroll down a tiny bit to get it on the board before we get the picture out of the way. So for the blue part, well, let's start with the red part because it's on the bottom. Bottom half. So on this one, we're going to integrate from a y, it's y now, right? It's with respect to y, it's dy. So a y value of 0 to a y value of 2. Those are going to be our boundaries there, 0 to 2. And it's just a disk. We don't need to subtract out a hole in the middle. So it's just pi r squared. And the r in this case is this curve on the right here, x equals y. So it's pi times y squared. Put the pi out front because it's a constant. And then y, you could even think y minus 0, right? Y, x equals y minus x equals 0. So you could even write it like this. But of course, y minus 0 squared is just y squared. And then dy. That's it. That's the bottom half. That's the whole thing. That'll turn into that cone volume. And then for the top, I'm saying half. It's not really a half, but top part. I'm not saying they're going to have equal volume or anything. Oh, and I should stay consistent with color here. So that in blue is going to be, again, pi. And now we're integrating from 2 to 4 because a y value of 2 here to a y value of 4 here. And the functions are, the bigger x value is the one on the right. It's this one. It's x equals y, right? So it's y. So pi times big R squared, y squared. But now minus, instead of 0 squared, because we're not going all the way to here, we're just going to here. We're going to subtract that inside curve, which is the y minus 2 quantity squared. So y minus 2 squared is the radius, and we have to square that, right? So it's pi times big R squared minus pi times little r squared. And that's what it's going to, that's our setup. Whoops, so I do need that square. And the whole thing with respect to y, because dy is the width of those little rectangles or discs or washers. So now we just have to evaluate these. And we can add them together, right? Because it's the volume of the bottom piece plus the volume of the top piece makes the volume of the whole thing. So the bottom part's nice and easy. We're going to integrate y squared. And by the way, remember how the bottom was a cone we said, right? Well, watch what happens when you integrate y squared. You get 1/3 y cubed. And that y is r, right? That's like the radius of the cone. And we're integrating and then evaluating, times pi, right? And we're evaluating from 0 to 2, okay? And I'm just going to keep going on that one. Let's finish it. So if we plug in the 2, pi over 3, okay? And if you plug in the 2, you're going to get 2 cubed, which is 8, and then minus 0 cubed, which is 0. And so we get 8 pi over 3. That's the cone part on the bottom. And 1/3 pi r squared h, right? So the volume of a cone, if you think of it, is pi over 3 times r squared h. And so that's, you can see the pi over 3 in there. And then our r squared on this, because of the function we were dealing with, x equals y, the radius of the cone was 2, and the height was also 2. And so we had 2 times 2 times 2, and that's where the 8 comes from. So you could also have done this problem with geometry, but we're trying to learn the calculus setup. All right, so anyway, it does match if you did it that way. The top part, we have to, this integral is a little tougher. We're going to expand this. So it's going to be plus, and again, pi. We could have kept the pi out on the whole thing if we wanted. And then we've got 1/3 y cubed. Minus, and then, oh, you know what, I'm sorry. I need to do expand first. I said that, and then I didn't do it. I said in the integral. That's okay. We'll just do it up here in light blue. If you take y minus 2 squared, that's like y minus 2 to the 4th. And however you like to do that, but if you know Pascal's triangle, the 4 row is 1, 4, 6, 4, 1. So you could do y to the 4th times 1, right? 1y to the 4th plus 4 times y to the 3rd times negative 2 plus 6 times y to the 2nd times negative 2 to the 2nd plus 4 times y to the 1st times negative 2 to the 3rd and plus 1 times negative 2 to the 4th. And so I probably should show an intermediate step here. Let me move this down a little. So this is pi times the integral from 2 to 4 of y squared minus, we had y to the 4th. I'm going to distribute the negative here as I go. The next term is a negative 8y cubed. And when I distribute the negative that I mentioned, it'll be plus 8y cubed. And then I have a next term, the negative 2 squared is positive 4, so that's going to be plus 24y squared. But I'm going to distribute that negative, so minus 24y squared. And then the next term is a negative 8 when you do the negative 2 cubed, and then times 4, negative 32. So it'll be plus 32y. And then that last one, negative 2 to the 4th is plus 16. So it'll be minus 16 when we distribute the negative. And so it's all this dy, and now we can just go through. We could combine like terms here too if you want. It doesn't really matter. So we're going to plug stuff in at the end. And so 1/3 y cubed and minus 1/5 y to the 5th. This is going to end up being a little bit ugly. Plus y to the 4th over 4, but there's an 8 there, so 2y to the 4th. And then we've got y to the 3rd over 3, divided the 24, you get 8, so minus 8y to the 3rd. And then y squared over 2, divide the 32, so you get plus 16y squared. And then let me just shrink this up a little so it all fits. And then minus 16y. And that should be it from 2 to 4. And so when we plug that in, we have pi times, when you plug 4 in to y, well, maybe, the y cubes don't really go together that well. One's an integer, one's 1/3. So we could evaluate all that. It's going to be a little ugly. Problem was written to be a little ugly in hindsight here. But if we plug the 4 in, it's 64 thirds, and then to the 5th, 4 to the 5th is 1,024 over 5. And then, I mean, because it was 1/5. And then 4 to the 4th is 256. So times 2 is going to be 512. And then minus 8 times 64. That's 2 to the 3rd times 2 to the 6th. That's 2 to the 9th. That's 512. Hey, that's convenient. And then plus 16 times 16 is 256. So a lot of this with the powers of 2 here kind of cancels out. And then minus 16 times 4, which is 64. And then we have to plug the 2 in and subtract everything. So now we have 2 cubed is 8, so we have minus 8 thirds. I'm just going to write it below because I think a lot of this will work together well. 2 to the 5th is 32, so we have minus 32 over 5. Oh, but it's plus, right? Because I'm subtracting, and so I'm distributing a negative as I go through with the 2. And then I have minus 32. 2 times 2 to the 4th, so that's 32. And then I'm going to have a plus 8 times 8, which is 64. And then I'm going to have a minus 16 times 4, so that's minus a 64. And then plus 32. Okay, all that times pi. And again, a bunch of this cancels out, so it looks really ugly, but 512s cancel, these 64s can cancel, these 32s can cancel. And then we have to do a little bit of work here. So I don't know, I feel like I'm pot committed to this problem now. I have to like finish it, right? 256 minus 64, I think that's 192. And then minus, I'm going to put these together. Actually, no, I'm not. That's weird. I'm going to put these together, and I'm going to put these together. So the over 3s are positive 64 minus an 8. So that's 56 over 3. And then the over 5s are going to be, oh, wait, that was positive. And then the over 5s are going to be negative because the 1024 is greater. Minus the 32 gives me 992, I think, over 5. I think we could probably throw this in a calculator if we needed an actual answer here. So anyway, though, it's this times that pi out front. And for the other part, the 8 pi over 3. If you want to go any further on simplifying, obviously we could put these together. Oh, you get that 64 pi over 3 again, right? I guess we may as well write it. So I have 192 plus 64 thirds minus 992 fifths times pi. And it'll end up being, whatever that is, some fraction over 15 maybe, put it in a calculator. But we did the calculus part and a little bit of the arithmetic.